Okay, so we're talking about parameters for evaluating computer performance. That means how do we tell whether one computer is better, faster, more efficient than another computer? Better, faster, more efficient are all synonyms in this case. I don't mean to say three different things. I just mean to say in some way it performs better. The terms for measuring computer performance are these following. First, we're going to learn a bunch of terms so we can use them later. The CPU, that is the central processing unit of the computer. I hope you know what a CPU is. It's basically the processor. It's a synchronous unit, which means it's synchronized by an internal clock. Synchronous is from the Greek word syn, which means with, and chron, time. So it is with time, means it has a clock that runs it. It runs according to time intervals, which means that you can buy a computer that is, for example, 60 hertz or 60 gigahertz, which means that it runs, if it's 60 hertz, it means it runs 60 cycles per second, which means it has 60 clock pulses a second. If it's 60 gigahertz, it would be 60 billion cycles a second. If it's 60 hertz, it's that. If 60 kilohertz, it would be 60,000. If it's 60 megahertz, it would be 60 million cycles per second. That's the clock rate. We can call that the clock rate. So in other words, in order to understand there's a clock rate, you have to understand there's a clock. And the clock rate is the frequency of which the clock beats. And when we talk about the multi-cycle, we said that in the multi-cycle, some instructions take 5 clock cycles and some take 3. So we're talking about those cycles here. How many cycles are in there in a second? And we can measure these cycles in terms of, like I said, kilohertz, megahertz, gigahertz. That's how many per second. But there's also the inverse of that, which is the clock cycle. In other words, this was the clock rate, CR, the rate, the frequency. Now we have the clock cycle itself. So that would be the inverse. In other words, if there's 60 a second, then each one is a 60th of a second. So the clock cycle is a time. CC, clock cycle, is a length of time. How long each cycle is in seconds or milliseconds. So we might say, for example, it's 1 millisecond or 1 microsecond. A millisecond is a billionth of a second. And a microsecond is a millionth of a second. So if it runs at 1 megahertz, that would be the clock rate. The clock cycle is really should be called the clock cycle length. And the clock cycle length will then be, if it's 1 megahertz, it'll be 1 microsecond. Okay, some more terms that you need to know. Instruction count. That's the number of instructions that the computer performed for a given program. Actually, I should change. Number of assembly commands that were performed for I want to change this, for a given program. In other words, the number of commands that were performed for a given, in other words, the number of instructions, we could say. Let's change that also. Instructions that were performed for the given program. In other words, I could have a program that has 1 million instructions in it. Then the instruction count would be 1 million. How many commands are in my program? The cycles per instruction is an average. Obviously, some instructions are 3 and some are 5. And in other computers that we are also talking about, in other words, we're talking about any theoretical computer, they could be any number of instructions. Any number of cycles for instructions. You could have a 10 instruction, 10 cycle instruction. You have a particular instruction. Mishi, you need to be quiet. You have a particular, wait just a second. Trying to get a babysitter here.
So that's just saying how like complicated the instructions are.
How complicated the instructions are on for a given program for a given machine. Because if I have a program that just does all the very simple ones and does all instructions that are R-type, for example, in MIPS. In MIPS, the R-type is 3 instructions. So if all I'm doing is R-type, then the average will be 3. It's the average how many instructions, how many cycles it takes to do instructions. The average of that. So I take all the cycles that it took me to execute this particular given program. You take all the cycles that it took me, and I divide it by the instruction count. So, for example, if I had a whole lot of programs that were a whole lot of instructions that were 10, instructions that took 10 cycles, and I had a few that took 1 cycle, then the average might be 9. The average might be 9 cycles per instruction, even though there's not a single command on the computer that takes 9.
What are you supposed to compare that to? Like, why is that useful? Each program is different.
Because it's a way of comparing 2 different computers and sort of comparing apples to apples. We'll see how we use this. We're going to use these numbers in examples. Where was I? Okay, CPI of I, number of cycles required to perform one instruction of type I. So that's not an average. That's like this CPI, but it's for a particular one. In other words, in MIPS, the CPI of any R type is 3. The CPI of a load word is 5. So this I means for a particular I, for a particular instruction. This is an average. This is a particular one. CPU time is the time it takes for the processor to execute a certain program measured in seconds. In other words, I take a program, like my million-line program that I was talking about, that has 1 million instructions, and I run it, and it takes an hour. So that's the CPU time. It took an hour. Well, it's not really the CPU time if it took an hour, because there could be input-output that the CPU was idle for. So it's really just the CPU time, the time it took for the CPU to execute the program. It could be that this program was waiting for 3 hours before I typed in the number 7 to tell it what to do. So the 3 hours don't count. We only count when it's actually running, not when it's doing input-output, which includes writing to a file or reading from the screen, reading from a keyboard. It's measured in seconds. So there's something called CPU time. Well, right, sorry. This is CPU time. I don't know why I put a minus here. But CPU time is basically, like I just said, it's the clock cycle length in seconds. How long is a clock cycle times the number of cycles in the program, which we figured out. Well, we didn't figure out. We figured out the number of instructions, and then we figured out the average of how many cycles it is. But if we have those two together, we multiply them, we're going to get the number of cycles in the program. And that's what I do here. CPU time is equal to, in other words, how much time is the CPU actually working? It's irrespective of the input-output. It's the CC, which is the length of a clock cycle, times the average of the CPI. How long is your average instruction? And then IC, which is your how many instructions, instruction count. How many instructions are there in your program? That makes sense. But we can also say like this. We can say the CC is equal to 1 over CR, because we know that. That's what we said over here. Here we said the CR is equal to 1 over CC, but if you remember your math, I can multiply both sides by CC and then divide both sides by CR, and I'm going to get CC is also equal to 1 over CR. They're both true. It's always like that. I could also say, see, I wrote it here. I could also say CC times CR equals 1, and I could also say CC equals 1 over CR. That's what we're doing here. So once we say that the CC is equal to 1 over CR, I can replace this CC with 1 over CR and leave the other two. So I can say it's the frequency times the CPI times the how many instructions there are. That's the CPU time. And now we have basically a very simple statement that looks complicated, but it's really a very simple statement. And what we're saying is, if we have a benchmark program, what is a benchmark program? It's a program that I use to test my computer. I want to see if my computer is fast or slow. So I take the same program and I run it on 3 different computers. And I see which one runs it fastest. So that's a benchmark program. So we want to calculate the CPI, the cycles per instruction, which is an average for this program. So it's very simple. It's the sum, you can think of it yourself, it's the sum of all the instructions divided by the, in other words, it's the sum, the CPI for a particular instruction and then I is the number of times the instruction type I is executed in the program. So in other words, I have my R type. This is, for example, my R type, the CPI of R, times how many R's are in my program. I just choose R because they're all the same length. I could really say add. The add, how many times the add? How many times the, what's another R type? I don't know, subtract. Or what's another R type? I don't know. But what's the length of cycles for it? This is, remember, this is a particular cycles per instruction. And then how many instructions? And I add up all of those ones. And there's how many I have of the R, how many of the load word. And then I divide it by the number of instructions in the whole program. That gives me an average. Or I could look at this way also. I over, there's a particular, this is all, my impression, this is all a big mess. All you have to know is this middle part here, and it's very obvious. Obviously, the sum of all the instructions, you add them all together, and you divide it by how, it's the length of time of each instruction. Again, this is 3 for R. This would be 5 for a load word. And this I is how many times I have the load word, how many times I have the R, and I multiply those two together, and I get how many instructions are, this gives me how many instructions are being used in the whole program. This is all the instructions in the program, because this is every single I type, every single type, every single instruction type, or every single instruction example. Really, it's not a type. It's like add, load word, store word, branch, branch equal, branch, BNE, BQ, all the possible things. All of them added up, divided by how many total instructions there are in the program. That'll give you the average CPI. Fine, that should be clear. Now we can come up with the most basic measure of computer ability, computer
computation.
What?
Like computation ability.
Performance. No, performance. The most basic measure of computer performance. So millions of instructions per second, otherwise known as MIPS, which is funny because that's the same name as the chip, but has no connection. This is millions of instructions per second. So I can say my computer has a MIPS of 2, and your computer has a MIPS of 3. So yours is better, I might say. Yours has 3 million instructions per second it can do. Mine can only do 2 million instructions. My poor computer is slow. It's not as good as yours. Yours can do 3 million. We're going to see this measure is not ideal. Okay. Let's go on. The number of machine instructions that a computer can execute in 1 second. So, for example, the MIPS of a particular computer is the instruction count divided by the CPU time. in times a million. In other words, let's think about that. This is the instruction count. How many instructions it was able to do? Instruction count. So it did, let's say my program had 1,000,000 instructions. So it did 1,000,000 instructions. And the CPU time, which we just talked about how you calculate it, CPU time is simply, take all the instructions and add up all of their lengths of time that they took in cycles based on that particular program. So let's say the CPU time of my 1,000,000 instructions over here was 1 second. I did all those millions of instructions in 1 second. So it'll be 1 second times 1,000,000, all under 1,000,000. So the 1,000,000 and the 1,000,000 cancel out, and I get 1. But if in that same 1 second I did 2,000,000 instructions, then it would be 2. 2, then the MIPS would be 2. Very simple. But it's very simple. We're just saying how many instructions did it do in a second, but in terms of millions. But since we know that CPU time is this, we can start writing things a little. We can start playing a little bit with math, and we can say, well, look over here. We said the CPU time is also equal to 1 over CC times CPI times IC. So let's throw that into the equation. CC times CPI times IC. Once we see that, we can say, there's an IC over here and an IC over here. Let's cancel them out. And let's say, furthermore, what is CC? CC is simply 1 over CR. So if this is 1 over CR, I can put the CR on top, and that's what I get over here. So I get CR on top and
What is
CPI on
CC and
bottom.
CR again?
CR is rate, is the rate of cycles. How many cycles I have in a minute? In other words, that's in gigahertz. That's like
CC
gigahertz.
is the time length of one cycle,
Yes.
and
This-
the CR, like, how does that relate to it?
It's 1 over. Because this you might have learned in physics at one point, but like if you're talking about a wave, the frequency of a wave, it's the same thing. But 1 over, in other words, if there's 1,000,000 cycles, or let's think about 1,000,000 cycles in a second, then I would say that the frequency is 1,000,000 cycles per second. Fine, that's the frequency, that's the CR. But what is the length of each of those cycles? They each took a certain amount of time. That it took 1,000,000. In 1 second, I did 1,000,000 of them. How long was each cycle? Well, clearly it would be 1/1,000,000th of a second. If I did 1,000,000 of them in a second, that'd be 1,000,000th.
Okay.
But what is 1,000,000th in relationship to 1,000,000? It's 1 over, right? So the CR is the rate, which is 1,000,000 a second. The CC is the length of each of those. Well, that's obviously going to be 1 over the CR, 1 over 1,000,000, 1,000,000th. That's how long it is in seconds. Is that clear?
Yeah, thanks.
Now, but mathematically speaking, anytime you have 1 over x, I learned this in math. Whenever you have 1 over x equals y, you can also say x equals 1 over y. They're the inverse of each other. Doesn't matter which one you put on the left. Y equals 1 over x, or x equals 1 over y. It's the same thing. So that means when I have this, I essentially have 1 over c. I have a 1 on top here and a c over here. So I can replace this 1 over c with a CR. That's what I did here. And the ICs cancel each other out. So I get the cycle rate, which would be like 6 gigahertz, divided by the average of the average CPI times 1,000,000. So let's see if that's right. Here's my 1,000,000. Let's say the average, sorry, what did I write here? Here I didn't do that. I used this equation. Fine. Anyway, you should understand that this is mathematically correct, and it makes sense also. Why is MIPS obsolete? The answer, we're going to see, I'm going to give you an example of this, but in words, the answer is that different instructions require more or less time than others. In other words, this is just telling me how many instructions it can do. But maybe I've got a computer that has it does this program. My computer Nebuchadnezzar only does 2 instructions a minute. But those 2 instructions, it's able to compute the world. So simply saying that my computer does fewer instructions than your computer doesn't prove anything. Because maybe some computer has much more powerful instructions than another. I mean, assuming that that's not the case, assuming that all computers have more or less the same kinds of instructions, then it makes sense. But this can become misleading when, as the instructions become more sophisticated and more specialized, and it may be that I can do much fewer instructions, but I can get a lot done in those instructions. Is that clear? Questions, comments, disagreements?
So your more complicated instructions are just becoming like more and more multi-cycle, right?
Exactly. My more complicated ones will have many cycles, and therefore I can't do that many of them in a given time. But I don't mind because there's such great instructions that do so much. I have one instruction that computes pi to the millionth decimal place. So it's one instruction. It may take an hour, but it's just one instruction. It's one assembly line instruction. It takes 1 million cycles. So you're going to say that my computer is slow because it only does one instruction in an hour, but those instructions are really very powerful instructions. I mean, I'm giving a crazy case, but possible. There's another problem with MIPS, which is that it only refers to the CPU speed, where real applications are generally limited by other factors such as I/O. In other words, I may be interested in how quickly my computer can read from a disk. It needs to read from a disk to run my computer, to run my program. That program all the time is reading and writing to disk. So I take 2 computers, and one of them is slowed down because of one of them is very slow because it takes a long time to write to the disk. But I'm not going to count that. That's not going to be in the equation. I'm going to think of that computer as very fast because it's doing a lot of instructions, and I ignore all these input output. But really, input output is important, and I'm ignoring it. So this is the problems with this method. Okay, so the MIPS index depends on the range of processor commands and the composition of the benchmark program. Right. It could be that I have a program that wants to compute pi, and then my computer, runs that very long command, and then it turns out that he did only 1 command in that hour. Whereas somebody else's computer did 1 million commands to get the pi, and he took 2 hours. But it's going to look better. His computer is going to look better because it's going to say look how many instructions he did in those 2 hours. So many, whereas you only did 1 instruction in your hour.
So it's really like a useless benchmark.
Yeah, I mean, I'm giving a crazy example, but it's not useless, but it has its flaws. It has its flaws as the commands get more and more heavy and powerful, it becomes less. And if I'm comparing apples to oranges, and if I'm comparing one computer that has very simple commands, another computer that has very complex commands, it's not fair. It's not a fair measure. If I were comparing 2 very complicated computers or 2 very simple, then it might make sense. But again, we'd have to talk about input output also. So as I say, it depends on the range of processor commands and the composition of the benchmark. It depends on what the actual composition of that program is. Let us assume, so here I'm just going to give an example of what I just said. Let us assume that processor A has more complex assembly commands than processor B. It has A has got these super amazing commands, and B has just regular simple ones, which means that the instructions of processor A take longer because they're super complicated in execution in relation to instructions of processor B. B has very simple ones, so they take less time. It is clear that if we run the same program on the 2 processors, we will observe that the instruction count of A is less than instruction count of B, presumably. I mean, it's not clear. I don't know why, presumably, why he says it is clear. We should really say we can presume. I mean, I wrote that, but I guess Barur, he said. I would say presumably it's less. In other words, if I have these complicated instructions, it must be because I want to use them. And it must be that if I use them, I'm going to have fewer of them because they do a lot. They're not complex and useless. They're complex and useful. So therefore, I'll have fewer instructions on computer A. The instruction count will be less, even though he'll get the same work done as B. In processor A, whose instructions are complex, it is possible to execute a program with fewer instructions than the simple processor B. That makes sense. And so we can say that the millions of instructions per second of A is less than millions of B, which makes it look worse. Poor guy A can only do 10 instructions in an hour, and he can do 100 in an hour. But that's because these are more complex. However, this does not mean that processor A is less rapid than processor B. It could be that because he's got these complex things, he finished the job faster. But he did fewer instructions, so it doesn't look. It's not a good measure. So we have a different method of measuring. Oh, where am I? And the different one is called MFLOPS, which is million or mega floating point operations per second. And what I do here is I take a high level language and I and I say how many floating point operations can this program do in this benchmark program in a given time.
What do you mean by floating point operation?
I mean, well, everything you did, if you did the lab, everything you did in the lab was always int multiplication. When you did a mult command, that's 2 ints. When you did a div, that's 2 ints. This is actually a special command if you want to multiply 2 floats. And as you can imagine from what we learned in previous chapters, that's going to be much more complicated. Multiplying a floating point, you got to make the mantissa, you got to round it up, you got to, all that stuff that we did with multiplying floats, the hardware has to do. The hardware has to do. Again, not the program. The hardware is going to do that. So those commands are obviously going to take more than 5 cycles, maybe 20 cycles, maybe 60 cycles to do a division with the floating point numbers. So what we're going to do is we're just going to say how many. Take a given benchmark program. How many floating point operations did it have in this C program? Logically it should have 1,000. If it runs, it's going to have 1,000 times. It's going to do float multiplication or float division. By the way, what I just said should make you realize that if you're doing a multiplication in a program in C++ and you don't need a float, you should use an int. Don't just use a float all the time. It's actually going to make your program run slower. I mean, it doesn't matter. And, going to be instead of a billionth of a second, it'll be 2 billionths of a second. But it's not a big deal. But you should be aware that on a slow computer, it could have significance. The int operations are much faster than the float operations. So we'll take a given program in C++ and we'll say, how many times does this program have all its float operations? How many? It has 100? Let's see how long they took. Measure of how many floating point operations can the computer do in a second? This measure relates to high-level language instructions. It's the number of floating point operations. In other words, what does that mean relates to high-level language? Now, I'm not going to talk about assembly instruction. I'm not going to talk about a program written in assembly. I'm talking about a program written in C++, and we'll see why. Not by the example, we'll see why. Number of floating point operations in the program divided by the CPU time in total. Now, I'm ignoring the I/O again, but what's the CPU time? Remember, is the net CPU time. It's just what the actual CPU worked, not including time that I was waiting for the keyboard to be pressed. So I could have a program, for example, that did all kinds of actions, but it did just one lonely little floating point operation. So then I would only be interested in the floating point operation divided by how long the program took to run in its CPU. If it took an hour to run and had one float, then it would be, then I would have a very bad number of millions of floating point operations per second. It would be very small. I would have a very tiny number if that would be the case.
Is there a way to account for both the MIPS and the MFLOPS?
Yeah, you can calculate both on the same program.
Would that be an accurate way to calculate the speed and compare to processors?
Again, I would say that none of them are accurate. You just have to be aware of the inaccuracies of each of them. But this one is considered better because, why is this one better? Because instead of looking at every command, this is a key point. Why is this one better? Instead of looking at every command, we just look at a certain command, and that command is more or less uniform. In other words, on pretty much every computer, he's going to have a multiplication. He's not going to be able to make a multiplication of two floats. He's not going to make a more sophisticated way of doing that. He's not going to have like take four floats and multiply them together and get the result, and have a special command for a 4 multiplication. He's not going to have that because it would be stupid to have that because already the floating point operation is a complicated command. Normally, when you make complicated commands, you take simple ones and you combine them or something like that. You take a couple simple ones, you put them into one, you wrap them up. But you would never take, from a design point of view, you would never take a very complicated one and then make it even more complicated one. So we can therefore say that everybody's floating point commands will be pretty much the same level of complexity. So therefore,
your MFLOPS is still based on like the ratio of regular commands to floating point commands in your program. And if
we're going to compare two computers with this.
With the same program.
With the same program. We're going to compare two different computers with the exact same benchmark program. So it doesn't matter that it has only one in it, because they'll both get a bad score, but we'll see which one is better. We're only interested in which one's better. Right? Or if they have lots and lots of, imagine a program. I mean, ideally what we would do is we would take two programs that have a ton of float. We would make a loop and just do lots of floating point operations and run them on two different and see which one's better. And then we'll see, oh, this one is able to do it. Presumably, each one did its floating point operation in the same number of cycles, presumably. And yet this one, maybe not. Maybe this one's a little bit maybe this one has a little bit faster cycles, and this one shorter cycles, but it has a little bit longer. It takes a little bit more cycles than the other guy to do the same floating point operation. So we'll find out, did he gain or did he lose? By making his cycles shorter, but making the command take a little bit longer, was it a good idea or not? That's by in comparison to the older program, to the older computer. So again, problem of MFLOPS. The MFLOP is calculated relative to the runtime of a high-level language. Therefore, it depends on the compiler. So this is another aspect that we throw in now, another level of uncertainty. Before we were talking about assembly. When we were talking about instructions here, we were talking about assembly instructions. We were talking about, how many assembly instructions. Now we're talking about high-level language. How many times I asked for, I did a multiplication of two floats, and then I ran a loop on that. So we're talking about a high-level language. Wait a second. We're talking about a high-level language, and the compiler is now involved, and the compiler could be inefficient. It could be that one compiler just makes a lot of wasteful code. So therefore, and I can't use the same compiler. You can say, why don't you use the same compiler? Because every hardware has its own compiler. That's the definition of a compiler. It's particular to a hardware. So the compiler for one hardware could be worse than the compiler for another hardware, and that is a new factor that that ruins that biases this result. You had a question?
Why can't we have floating point operations in assembler?
In assembler. I thought you were going to ask. Why don't we just measure two assembly ones in floating point? And the answer we're going to see you're going to see exactly the answer to your question in the example here, but the answer is because not all computers have a dedicated floating point operation. Theoretically, I could, remember we learned the algorithm for multiplying floating points. I could create a pseudo instruction kind of, where when you multiply two floats, I actually run a series of commands in ints. I run a series of 25 integer commands, and I get you your result. So it could be that if I would go down to assembly language, this computer has no command for doing floating point operations. What does it do? The compiler simply, when I do a floating point operation, the compiler simply translates it into 65 different commands. That set of 65 commands gives me my result. When I look at the assembly code of these two programs, I won't see any floating point operation there because it doesn't have it. So then I can't compare the two computers.
If they're both taking the same input and doing the same output, shouldn't it take like relatively the same amount of time?
No, not if I compare a computer from 1975 to a computer of 2020. I would get different. They would work different speeds. I hope. No, we would not have this.
Yeah, but then that would obviously show the 1975 computer is worse, which is what
exactly
we would be expecting.
Yes,
that's what we're expecting.
Yes, we're trying to create a way of getting what we expect. Any system, any method that we have for comparing computers should produce the right results when we're comparing things that we know a priori are in fact, one better and one worse. So yes, it will. But when we have two modern computers and we compare them, the results will be slightly, haven't you ever asked yourself this question? Should I get, an i5 with 16 gigabytes? Should I get an i5 with with 32 gigabytes of memory, or an i7 with only 16 gigabytes of memory? Which is better? Is it better to have, or should I get this graphics accelerator or this graphics accelerator? Which is better? So they try to benchmark they try to take a program and run it on both computers and try to measure it. So we're trying to measure it in mathematical terms. What you could just say we're going to see that in the end, the best way of measuring is just by human feel. I played this complicated video game on this computer and it ran better than on this computer. But of course, that doesn't tell you much because I might want to buy the computer for doing compiling of complicated programs, and compiling of programs requires different parts of the computer, different commands, different aspects of the computer are being used than playing a video game. So, we're always interested in comparing computers. There are many ways of comparing, and actually I think the conclusion here is the most accurate measure is to compare the most accurate measure is to compare CPU time of the same programs on each processor. Of course, it's not going to work on a video game, which is completely I/O dependent. It depends on how fast you press the fire button, how fast what you do in the program. But if we have a program that just does number crunching, so then I can take the same program that does number crunching and just see how long does it take on this computer, how long does it take on that computer. That would be actually the most accurate. Right. But if we did it this way with a game, then it would take into account I/O. That's what's written here. It will take into account I/O if it has I/O in it. So therefore, as long as I have the same player, I get the same player to play, whatever it is, Minecraft or Fortnite, and let him play on these two computers and see, in order for him to get from level 1 to level 6, does it take him 3 hours? It takes on this one it takes him 3.5 hours. So so you could say the one that took him 3.5 hours must be a slower computer. Maybe not, and maybe he just was tired that time and he did it worse. But that would be the CPU time is considered like actually the best way, but it's not mathematical so much. Actually, this is wrong that I write CPU time because then it won't take into account. I just said CPU time. It should really, I have to check that. It should really be time. It should really be the runtime. It should be the runtime of the same program. Then it will take into account I/O. I wrote here that it's desirable to run several test programs. So anyway, the two measures we have seen are MIPS and MFLOPS. They are artificial and problematic. Therefore, we will attempt to compare processes. Therefore, we will attempt to compare processes in as similar conditions as possible. For example, the same test program, the benchmark program, the same compiler efficiency. Try to have a compiler that's equally efficient. As when using these things, try to have good compilers, the same type of compilers. Try to have the same program, obviously. And then I said here that also runtime is really the best way, but that's not mathematical so much because it depends on so many factors. So maybe we can start this example. I don't think we can finish it. Here's an example. This is good to see the example now because it gives you an idea of what we're doing. Let's say we have a computer that has, on a particular benchmark program, 43% of its commands are of type R. In other words, they're adds, let's say. I don't know. Actually, I'm going to change this. They're add. Let's take a particular command. 43% are adds. 21% are loads, 12% are stores, and 24% are branches. And the CPI of these particular instructions are 1, 2, 2, and 2. That means a branch takes 2 cycles. A store takes 2 cycles. It's obviously not MIPS. It's a different computer. Fine. Now, what's our question? It turned out that a quarter of the ALU commands use as one of their operands a datum that was brought in a previous load command and is used only for ALU. In other words, a lot of times, 25% of these 43 are actually preceded by a load command. 25% of these are preceded by a load command. So the question is now, the engineers come back from their laboratory and they tell us, you know what, we can change the computer. We can make a new command called MEMALU, which in one shot will do a load and an add. Now, what is this going to be good for? Well, it's going to do this load and the add in, why don't I see the question? Wait. Oh, did I? Yeah. They're going to do, sorry, I was on the wrong page. It is proposed, in other words, by a set of engineers, to add to the set of processor commands the ALU command, which performs direct operation between a register and a memory datum. And this instruction is in place of a load and the ALU instruction between 2 registers. We will call this MEMALU, and this command will be executed with a CPI of only 2. Now, why do I say only 2? Because normally, if I would do a load and then an add, how much would it take? We'd take a load, would take 2, and then an add would take 1, take 3. Now I'm going to combine these and do it for cheaper. But of course, I can't combine all of these. It's only 25% of the ALUs are combining with the load. So that sounds great. Let's do that. Even if we get 25% improved, that 25% got improved. So that's great. But there's a cost. The CPI of a branch will change from being 2 to being 3. Somehow,
why does that affect the branch command?
It's just given in the question. Whatever. The engineers, in order to do their magic, they had to screw up the branch command. I don't know why. They used the same hardware, and it ended up that the branch command became longer. Obviously, they could have added hardware, but they didn't. They rewired things, and it came out the branch command and became 3. It just happened. It's a given in the question. Assume that the program has 100 instructions and that the CC is constant. That's very important. The CC is constant. That means the speed, the length of time that it takes to do a cycle doesn't change. If that changes, that also could affect the results. Find the number of clock cycles before and after the change. So basically we do like this. We say, take our 43 and take a quarter of it off. So we're left with 32, which means we took off 10 3/4. Those 10 3/4 are now going to be done by this command. But also 10 3/4 are going to go away from the load because remember we're combining an ALU with a load. So this becomes 10 1/4 because 21 minus 10 3/4 is 10 1/4. And the store stayed the same and the branch is the same number of branches, 24 and 24, but it went from a CPI of 3 to a worse CPI, CPI of 3. And now, okay, now why do I say 43? 43 was percent, but he was very nice in the question and he said, assume that there are 100 instructions. Well, if there are 100 instructions and 43% of them are adds, then I know that 43 of them are adds. If it would be 200%, then it would be 86. But whatever, he did it easy. If he did 107 commands, it would have been very hard to calculate these numbers. They would have been small. They would have been decimal with decimal points. But in any case, we have 43 is before. So now we want to calculate. Well, let's calculate the CPI of the what did he say? Calculate the clock cycles. How many cycles are we going to have for this program? Well, it's very simple. How many? 43 times 1 plus 21 times 2 plus 12 times 2 plus 24 times 2. All those together, that's how many cycles and how many that's a total number of cycles. How many am I going to have here? Very simple. 31.25 times 1. 10, all these numbers times, and I'm going to get. And just which one is worse. So let's see. So if you add them all up, we're going to get that, where do I have it? Wait. According to the problem, right, we said 32.5 remain, 25% go to this. So we get the mem ALU will be 25% of this, which will be 10.75. That means the load goes down to 10 3/4. Notice the total number of instructions dropped after the change. Well, what was when we added all these things together, it obviously added to 100. Sorry, the total number of instructions. Instructions went up to 100, was 100 here. How many instructions do I have here? If I add up all of these, I'm going to have less than 100. Why? I'm going to have 89 2/5. Exactly the amount that I removed because I took 2. For every 2 between these two, I took away and replaced with 1. So I have fewer instructions. So now I have only 89 instructions. Now, fine. Now we can check the number of clock cycles. And that's what I was doing before. By simply multiplying this times this times this. So we get, over here, 32 1/4 times 1, 10 times 2. And here's our new instruction, 10.75 times 2. So this is our new computer. And it's 170 instructions. The old computer was 43 times 1, 7, all these numbers was added up to 100, but times the different amounts for each type of command, and I got 157. So which one's better? Well, I can right away say that since the clock cycle is the same, and the new one has more clock cycles to the same program, it's obviously was not worthwhile to make this change. The CPU time of the old one is less than of the new one. Conclusion, it would have been better not to create the new command. But I just did one last step, which is I multiplied the 170 by the clock cycle length, because the clock cycle length, if it would change, it could have an effect here. Maybe the clock cycle got shorter in the new computer. If it got shorter over here, if this number is instead of, a millionth of a second, a billionth of a second, then the new computer is better, even though it has more cycles. So that's why he added that in. In this case, he said that CC doesn't change, so I can remove it from the equation. Okay, we'll stop there.